Today, I'm going to follow up on my last video by talking about two techniques you can use to better help you solve Thévenin circuits or arrive at Thévenin equivalent circuits. So let me start with the first one, which has to do with independent versus dependent sources. I said in the last video that you have to be careful if there's dependent sources in your circuit. You need to make sure that they're self-contained and all controlling variables rely within your black box or your dashed line here. But for this first technique, I'm just going to talk about what happens when your entire circuit, everything within these dashed lines, is comprised of only independent sources. So in that case, if there are no dependent sources, there is another path you can follow to find the Thévenin resistance or the Thévenin equivalent resistance of your circuit. If a circuit contains only independent sources, you can find the equivalent Thévenin resistance by quote-unquote zeroing that source. In the case of a voltage source, zeroing the source means setting the voltage equal to 0 and drawing the equivalent circuit, and then finding the input resistance or the Thévenin equivalent resistance. Voltage sources have, ideal voltage sources that is, have 0 resistance equivalently. They just apply a voltage, but they don't add any resistance to the circuit. So, if this 15-volt source, for example, and this is the example circuit from my last video, if this 15-volt source were instead 0 volts, I could equivalently draw a short circuit here. When you're finding a Thévenin equivalent resistance, you don't care about sources or these elements that add energy to the circuit. You're removing them and looking only at passive elements. An independent voltage source equivalently acts as a short circuit because it adds 0 resistance. So our equivalent circuit that's left over is just our 100 ohm resistor and our 50 ohm resistor, and we're able to then find the Thévenin equivalent resistance. We just have a 100 ohm resistor and a 50 ohm resistor in parallel. 100 times 50 divided by 100 plus 50, or 33.3 ohms. And if you watched the last video, this is the same result for the Thévenin resistance that we got last time. Clearly 1/3 of the total voltage must drop across the 50 ohm resistor, so we can easily see what the open circuit voltage must be across these terminals, and it's 1/3 of the source, which is 5 volts. So I'll just quickly draw out the final Thévenin equivalent circuit, and if you recall, this is the same result that we got in the last video, finding this model through slightly different methods, but it's the same model. This is a 5-volt source in series with a 33.3 ohm resistor. This is our Thévenin equivalent circuit. So the whole point of this example was just to show that there's an alternate method you can use to find the Thévenin equivalent resistance, given you have the condition that your original circuit contains only independent sources. And although I didn't cover it here, it actually doesn't matter that our original circuit contains just a voltage source. Your original circuit can actually contain voltage sources or current sources or some combination of the two. The original circuit doesn't matter. It's just that the Thévenin equivalent circuit is comprised of a single independent voltage source and a single series resistor. All you need to use this technique is the condition that your original circuit contains only independent sources. So that completes this example. I'm going to go ahead and go over one more quick example, and that's how to solve for a Thévenin equivalent given that you have dependent sources in your circuit. I have a 10 volt independent voltage source with a 5 ohm resistor, and we're monitoring this current through the resistor and calling it IX. Then there's a dependent source that depends on this current IX, and it delivers 2 times IX. So no matter what the current is that flows through this 5 ohm resistor, there will be a current generated here that's twice that size. Then we have a 10 ohm resistor and shunt here. It's, again, 10 ohms. And then I've drawn this dashed line around here, so this is going to be the circuit we want to model. And we have the terminals here with respect to which we want to create that model. So remember, to create a Thévenin equivalent circuit, we're concerned with Thévenin resistance, open circuit voltage, and short circuit current. So we can't zero the sources because there's a dependent source inside. So we're going to go ahead and try and find the open circuit voltage and short circuit current. I know that VOC will be related to whatever current flows through this 10 ohm resistor, so I'm just going to say that VOC equals the total current through it, which is the sum of these two currents, IX and 2IX, IX plus 2IX, times that resistance, so 10 ohms. To look at IX, I'm going to try and do a voltage analysis, so a loop analysis. So we have VOC, we have the source voltage. The missing link in that loop is the voltage across the 5 ohm resistor. So Kirchhoff's voltage law tells us that, we'll say, and 10 volts minus VOC equals IX times 5 ohms. What that means is that we step up 10 volts, and that total 10 volts has to be dropped, so some will drop across 5 ohms, but all that's left is VOC. So another way to look at this as the voltage across the 5 ohm resistor plus VOC equals 10 volts, and the voltage across the 5 ohm resistor is IX times 5 ohms. So this is a KVL equation. And then I'm just going to solve this for VOC by substitution. So what I really have here is that, therefore, IX equals 2 minus 1/5 VOC. And then I'm just going to substitute this back into the original equation, substitute IX in so that I have a formula that only contains VOC. And then what I get is essentially that, well, we have VOC equals 30 IX, and then we just bring that in, equals 60 minus 6 VOC, so 7 VOC equals 60, and VOC equals 8.57 volts. And this is our open circuit voltage right here. So this is half of our solution in finding our model, because V open circuit is also V Thévenin, and now I just need a Thévenin resistance, and our model will be complete. But keep in mind, because we have a dependent source in here, I cannot just zero the sources. I need to find the short circuit current. So the equivalent circuit model for that is going to look like this. But then what I'm going to do is short these terminals together, and this is ISC, or I short circuit. So the nifty thing in this case is that clearly this 10 ohm resistance is no longer in the circuit, because we've put it in parallel with an ideal conductor, a perfect short, a 0 ohm resistor, which equivalently is just the short. So anything in parallel with 0 is just the 0. So this 10 ohms is no longer here. And that makes a current analysis very easy, because it shows that IX summing up with 2IX equals the short circuit current. But what we also know is that because there's a short here, this node right here is actually the same voltage node as this right here. This is a wire that goes all the way around. And because that's a short, because it's an ideal conductor, what that tells us is this point and this point have the same voltage, meaning that this side of the resistor is touching this side of the 10 volt source. So that tells us that this full 10 volts is dropping across 5 ohms. But in that case, we automatically know the current flowing through the 5 ohm resistor. It's just a quick Ohm's law, 10 volts by 5 ohms is 2 amps. That tells us immediately that Ix is 2 amps. But then in that case, we know what 2Ix is. 2Ix is just 4 amps. But I said that I short circuit would equal 3Ix, or the sum of Ix and 2Ix, and that tells us very quickly that the short circuit current is 6 amps. And we know that our Thévenin is just VOC over ISC, which is 8.57 divided by 6 amps. In other words, our Thévenin is 1.42 ohms. And so to draw a quick equivalent circuit model, Thévenin equivalent that is, let me scoot this up to make sure you can see, we have 8.57 volts and 1.42 ohms. And this is our Thévenin equivalent model for our original circuit up here in this box. So I know this was a lot. I'll try and cut this down to be a shorter video if I can, but I hope this was helpful. Again, let me know if you guys have any questions or suggestions, and I'm hoping that next video I'll talk about Norton equivalent circuits. So I hope you guys have a great day.